In the first part of this video lecture, we have already seen what it means for an event to approximate another one. Then we have seen a theorem that an event in the sigma algebra generated by a certain algebra can always be approximated by events in the algebra. And we're going to give two different proofs. In this second part of this video lecture, we're going to see a proof using outer measure. Outer measure, for your reference, is a tool that we used in a previous video lecture to prove the Carathéodory extension theorem. As a brief reminder, the theorem we're going to prove is for every event B in the sigma algebra generated by a certain algebra, and for every epsilon positive, we can always find a set, an event in the original algebra, and the algebra is usually much more simple and transparent to describe, such that A offers a good approximation for B. So if we restrict the measure mu to this algebra A, then of course this restriction will satisfy the definition of what it means to be a pre-measure. Then we define for every subset of omega, that we call here E, the outer measure of this omega will be the infimum over all different ways to cover E using an infinite sequence of events or of sets that belong to this algebra A. We take a sequence of sets AN whose union contains E, that's what it means, that it covers E, and then we sum all those measures, and we try to do that in the most economic possible way, meaning we take the infimum. This is the definition of outer measure. Then Carathéodory's lemma says that for every set B or every event E in the sigma algebra generated by this algebra A, the measure mu of B is the same as the outer measure mu star. Well, the lemma says the set of measurable sets, if you recall the lemma. If not, you can pause this video now and go back. The set of measurable sets forms a sigma algebra. That sigma algebra contains A, and if we restrict to that sigma algebra, we get a measure. So necessarily, the measure we get, it coincides with this measure mu on all the sigma algebra generated by A. And that is what is written here. The measure mu that we started with and that we restricted to A, and then extended to all subsets of omega by taking the outer measure. If we now look at the sigma algebra generated by A, which is much larger than A, but normally much smaller than taking every subset of the sample space, omega, okay, we have this equality here for sets B in the sigma algebra generated by A. Now observe that this measure is finite because mu is a probability measure or a finite measure for the purpose of this proof. Finite measure would be enough. And therefore, this infimum here is finite. And when an infimum is finite, that means we can find a sequence here in this space defining the infimum such that that sequence will come close to attaining the minimum and satisfy this requirement. Namely, the set B will be contained in the union of that sequence, and the sum of the measures mu evaluated at the terms of the sequence will be less than this infimum plus epsilon. And note here we are introducing an epsilon that was given to us arbitrary. To be consistent with the lecture notes, we can even put here epsilon over 2 if we need it. And note that this here is finite because mu is a probability measure and epsilon is just a finite number, and hence we can take a number k such that the tail of this sum, meaning summing only the terms after k, is also small. And I'm also taking here epsilon over 2. To conclude, we take A to be the union where n goes from 1 to k only of a n, and since this is a finite union, this set A is in the algebra. And now here comes the magic. We're going to approximate this measure of difference, or the measure mu at the symmetric difference between A and B, by the measure mu of the symmetric difference between A and C plus the measure mu of the symmetric difference between B and C, where C is this union here that contains B. We can do this. This inequality is, let me go back, this one here that we saw in the previous part of these lecture notes. Now, A is a subset of C, okay? And why is that? Well, C is this infinite union of a n where n ranges from 1 to infinity, and A is also a union over n, but n ranges only from 1 to k. And moreover, B is also a subset of C, and you can see this here, that's by definition. C was introduced, the sequence AN was introduced exactly because of this definition of infimum here that was related to the outer measure of B. And because of this property that A is contained in C, the symmetric difference becomes simply the measure of C minus A. And likewise, this becomes the measure of C minus B, and we can relate them to what we saw already. This C minus A is exactly is contained in this ones that we're missing here. So this is a less than epsilon over 2, and for a different reason, C minus B is, we can bound here also by epsilon over 2. The full details are in the lecture notes. This will conclude the proof of the theorem, because then this is less than epsilon over 2, this is less than epsilon over 2. So we have just shown that this measure of the symmetric difference is less than epsilon, concluding the proof.